Hey, early last year, I bought a laptop, and specifically I bought this laptop. This is a Huawei MateBook Pro. It's very cheap, and it has acceptable specs for the price. Oh, it's not playing. The webcam pops out from between the F6 and F7 keys, which is an incredibly cool gimmick, and the main reason I bought it. There were no speaker notes on my screen. Hold on, sorry. Now there are. Everything on it worked when I installed Linux on the first day, because it's 2020, and that's how things work now, except for the fingerprint sensor. In the power button, there was a fingerprint sensor, which is really convenient. For the 5 minutes I had Windows on it, you can unlock Windows, and it's fast, and you don't type in your password. And I wanted to know why it didn't work, and I wanted to make it work. So we need to talk a little bit about the history of fingerprint sensor technology. This is, oh, okay, now it works. This is the bad old days. This is an IBM Flinkpad, and it has an optical fingerprint sensor. Unlike the modern ones, it works like the arm of a photocopier that moves along under a piece of paper. So you scan your finger down it slowly, and it pieces together an image of the fingerprint like that. And they're pretty unreliable and pretty slow. You have to get the scanning speed exactly right. And these only ever really were popular in business model laptops. They never came into consumer devices. But they had very good Linux support. There was the ThinkFinger was the original project, and then libfprint, which made these work really well. It just plugs into PAM, and everything is great. And in 2013, Apple introduced the iPhone 5S. And this had a new type of fingerprint sensor. This is a capacitive fingerprint sensor. So the scanning technology is the same as a multi-touch touchscreen, just made really small. The same way it senses where all your fingers are, it's the same scanner, it's just sensing where all the ridges of your finger are. And this capacitive sensor is much more convenient, it's much faster, you don't need to swipe your finger at the right speed. And so it was quite popular, and it was good in the iPhone, and it made its way into Android phones, and then into laptops, and this time not just the high-end business laptops, it made its way into consumer laptop models. But these sensors never really ended up being supported on Linux, despite a lot of people online saying, hey, I'd love to be able to use this. Can anyone make a driver? It just never happened. And the reason for that is kind of hidden on this Apple announcement page, where it says your fingerprint can also approve purchases from the iTunes Store, the App Store, and the iBook Store, so you don't have to enter your password. And if you used iOS before this, and you think about it, it's kind of weird, right? Because you used to have to enter your Apple account password to make a purchase. You're authenticating with Apple's servers to, use your payment information. You're not just typing in your phone PIN code. So to be able to do this authentication, how are they implementing that? There's a few approaches. They could just trust the phone when it says, yeah, I just scanned the fingerprint, I unlock the payment information. But that's probably not a great approach. You lose the security boundary that's in place here. You could do what is arguably the equivalent of the password model, where you just send a picture, you scan the fingerprint, and it gets the picture of your fingerprint, and it sends it to Apple's servers. And Apple's servers would have all of everyone's fingerprint in a database, and they would match it against that. But that doesn't work very well because of this situation, right? When Apple's servers are hacked, or the servers of some website with even worse security, the step 3 on have I been pwned needs to be modified, because you can't rotate this credential. You can't just change your password, right? So having everyone's fingerprints on Apple servers is a bad idea. And ideally, given that you can never rotate this in your entire life, and malware exists, and people run malicious code, ideally, I wouldn't actually have a picture of my fingerprint stored in my phone. Right? Like iOS jailbreaks exist, the vulnerabilities that enable them exist. So if someone can get my fingerprint with that, then again, I can never rotate this credential, and that's pretty annoying. So there's a third way to implement this, and this is what Apple did with the iPhone, which is called a secure enclave. And so this is a separate chip off to the side of the main iPhone CPU, which it has its own storage where it keeps the fingerprint image, and it only runs trusted signed code with a very small attack surface. And that code will read images from the fingerprint sensor, which it's connected to. It'll check it against the image that's in its own storage that iOS can't read. And if it likes what it sees, it'll sign what's called an attestation using a private key that's also only it can read. And this attestation is just a signed bit of information that says, yep, I just scanned the fingerprint, it matches. And that can get sent to the phone, which can verify, okay, cool, I just saw a fingerprint, unlock the OS. But more importantly, you can send that to Apple. And you can send it to any other website to say, yep, I just verified this biometric identity thing. And so this model works really well. And when it came to laptops, Microsoft encouraged the laptop manufacturers to bring this secure enclave model as well as the capacitive sensors. They call it Windows Hello in Microsoft land. And you can use it not only to unlock Windows, but also to unlock your BitLocker keys using the secure enclave and to log into Azure AD. But it's a bit more complex than the model I just laid out. SGX, which is the secure enclave on Intel CPUs, isn't some chip off to the side that's plugged into the fingerprint sensor and has its own storage. It's an execution mode of the main CPU, which can run code that's signed by Intel, and if the code is correctly signed, then it can access special storage that only SGX applets can read. So that's where they keep the fingerprint template and a private key for signing attestations. But it doesn't talk directly to the fingerprint sensor. It's not a Windows driver. It can't actually talk to devices in the chip in the laptop. So there is still a Windows driver that talks to the fingerprint sensor, but there needs to be some sort of secure tunnel between the secure enclave applet, the SGX applet, and the microcontroller in the fingerprint sensor. And that tunnel needs to be encrypted so that Windows can't see the fingerprint images, and it needs to be authenticated so the sensor knows that it's talking to the legitimate SGX software, because that's the only software that can be trusted to look at a fingerprint image and not leak it in this model. So my goal in making the fingerprint sensor work on Linux, it's elevated from reverse engineering and writing a driver for some hardware to breaking some security, right? Because we need to break this model to be able to use it on Linux to get images from the sensor in normal user space software. So that's what I went into this research trying to do. I'll go over this quickly because we're short on time. This is an ACPI tab. This is how, when your operating system boots up, it knows what devices are plugged into it, with the exception, obviously, of hot pluggable devices like USB ones. But this, you can see here, there's a serial peripheral bus, which is defined for this GXFP, which is the Goodix fingerprint sensor. And so this is the physical and electrical connections that define a stream of bytes that the operating system can exchange with this hardware device. And so it knows how to exchange a stream of bytes with this device. Obviously, this doesn't say anything about what protocol you need to speak over that. So we still need to reverse engineer the Windows driver to figure out how to actually talk to it. So I did that, right? I installed Windows again, and looked at the driver that got installed in Ghidra, which is what I was using at the time before I discovered the magic of Binary Ninja. And it's a massive DLL file, and it has a bunch of calls to logging functions, which are really helpful because they all have the name of the calling function when it's making a log message. But these logs never actually got produced at runtime when I was using the fingerprint sensor. So the first thing I did was reverse engineer how to enable the logging, and that was quite simple. There's just a registry key that you can flip on. This was my first real binary reverse engineering project outside of very basic CTF challenges. And I found that having something like this, which is a completely untime-constrained project where I can mess around with trying to understand a binary without the time constraints of a CTF, is a much better way to learn binary reverse engineering than in a CTF. I don't recommend that at all. And I was basically useless at it, having just done it in CTF contexts. So yeah, I can get the logs out, and these logs have some information about what the driver is doing at runtime when it's running on Windows. One thing that's useful in these logs is there's a little table of different types of message. So you can see like IMA is short for image, FDT, fingerprint detection, and so we have these numbers, but we don't have like the full messages that are being exchanged. We don't have full dumps of all of the packets in and out of this device, or bytes, whatever they are. And so I like that because I'm trying to implement this protocol. So I used x64 debug. I'm not a Windows person, and I chose x64 debug somewhat at random, and I had a lot of issues with it. It seems to have a lot of undocumented limitations. If there's a better thing I should be using, please let me know. But what I can do, right, is once I've figured out the SPIes, send and receive functions that just send messages back and forth over the stream of bytes. You can hook those with breakpoints in the debugger, and instead of normal breakpoints where you just stop for interactive checking it out, you can set up breakpoints that will just log, the memory that's pointed to by this register for the length of this register, and that'll log it into a x64 debug log file. And with that, what I decided to do, and I found this very useful, and I highly recommend it if you're doing any binary protocol reverse engineering, is I put it into Wireshark. You can see we've got these, I've got fake 1.1.1.1 and 2.2.2.2 UDP packets. That's not necessary, but it was the easiest way to get it in there, just generating a PCAP file with that. And so you can see the stream of packets, and all of these names are from a little Lua script I wrote. They have a really simple API for writing scripts. They're called dissectors, which will figure out what's going on in the binary protocol and display it like all the standard protocols. And especially useful about this, right, is that if you're going to be implementing your own version of your own thing that implements the same protocol that you're reversing, once you've figured out the protocol, you can run your new code through that and check it against, does your dissector see the right thing, or is there a bug in your code that's making it wrong? That's a really good way to cross-check your work when you're doing this sort of thing. And so these messages are all pretty boring. Like I said, these names of these things are just from reverse engineering the Windows driver, matching things up to, if it's sending this, then it logs, I'm going to send a thing with this name. So with that, all of these things are, these are boring. These are the initial startup messages when it's setting up the fingerprint sensor chip. Where it gets interesting is when we scroll down to here, and we see TLS 1.2 client hello. And this is insane. As an industry, we have been telling people for so long not to roll their own crypto, right? Don't just grab AES and assume that it does everything you need for your, it has all the integrity and everything that you need for your protocol. Just use some fully featured protocol that actual cryptographers have looked at and made something that will suit your use case. And so we've gone too far, because now there's TLS between my CPU and my fingerprint sensor in my laptop. You can see it's not normal TLS, it's TLS PSK. It's a standard type, but it's not what you're used to in web browsers. So PSK is short for pre-shared key. That means there's just a big, long, random key that both sides know in advance. And if during the handshake process, they can prove to each other that they have this key, and if they do both share the same key, then they'll set up a secure, authenticated, and encrypted channel between the two sides. And so how this works in a laptop context, at the Huawei factory, they will generate a big, long, random password for each laptop. They will stamp that into the chip of the fingerprint sensor and into the SGX storage that the Enclave can read. And then both of those sides can prove to each other who they are and establish a secure connection. But the rest of the stream, all of the stuff in Wireshark, it's not encrypted, right? The only other encrypted packet, apart from the handshake, is when you request an image with a clear text Windows driver message, it responds with the TLS application data instead of just an image. And this is great, because there's only one packet that's encrypted, only one packet that we need to figure out the coordinates of, but obviously it's the important one, right? If we're writing a fingerprint sensor driver, we need to get an image from the fingerprint sensor. But we have this whole attack surface of commands that aren't encrypted and aren't authenticated, more importantly, which means we can try and attack something, right? Because of this symmetric model with TLS PSK, we could do it. We have a choice for how to approach this. We could attack the Enclave side. Because SGX is just a special operating mode of the main CPU, the whole Meltdown and Spectre family are applicable here. Especially since I can downgrade Windows and I can choose to have worse Intel microcode and things that don't have these patches. And after I did this research, there was Plundervault, which is probably even more useful for the specific attack. But that's not what I decided to do. I decided to attack the firmware of the fingerprint sensor itself to get the PSK. And like I said, all of these unencrypted messages, unauthenticated, we can send these, and we can talk to the chip and do whatever we need. So specifically, the one that caught my eye, we have this table of the abbreviations for the different type of messages, is OXF, UpFW, which is short for update firmware, right? We can actually, the Windows driver, when it starts up, it asks the chip for its version, firmware version. If it doesn't like what it sees, it'll send it new firmware from a blob that's inside the DLL. And this blob, if we just look at it in Ghidra, we can pull it out, and it's a totally normal-looking thumb assembly blob. We can tell from the firmware version name that it's for an STM32F411 chip, which is something where you can just get the data sheets and find the addresses of all the peripherals. So I reverse engineered this and checked in how the firmware update algorithm worked, and I confirmed, like, there's no TLS, there's no signatures on the firmware blob itself. It's totally just the Windows driver can send a firmware and have it be on the chip. So rather than writing a whole new open source firmware for this fingerprint sensor, what we can do is just add a backdoor to the firmware. Right? We can do this, which is just a little function that replaces the handlers for one of these messages, the one that I hadn't seen used by the Windows driver. And instead of doing whatever fingerprint sensor stuff it's supposed to do, it's just an arbitrary read primitive. If I want it to have a vulnerability, I can just write some code that is the vulnerability and compile this with the right GCC, object copy out just this one function, put it on the end of the firmware with the right alignment, and then hex edit the address for the handler function for this type of command, and hook the Windows driver in the debugger to make it upload our firmware instead of the original firmware. And this works, right? Once you upload this custom firmware, I can send it messages asking for an address I want the memory at, and I know the address that the PSK should be from reverse engineering, so we can get the PSK out. And that's the PSK for my laptop. If they're doing things right, then it's a completely random PSK, and this is different to all other laptops. I haven't checked. I assume that's the case. But because this is standard TLS PSK, we can just put it into Wireshark, pre-shared keybox in the TLS settings, and decrypt the stuff. So where we used to have application data when we were getting an image, then now we have an image data. And this is really cool. We get this big blob of bytes, which from the Windows driver I can see, and from looking at it, I can see it's just a raw bitmap. And we can plot that bitmap, and it looks like this. And if you've ever seen my finger, you'll know that it doesn't really look like this. And I scratched my head, and I went back and I reverse engineered the bitmap unpacking algorithm from the Windows driver, and I decided there was something wrong there, so I looked at the bitmap packing algorithm in the firmware, because I've got both copies of this. And there was actually a Ghidra bug, which was slightly affecting things, but even so, after getting past that, this is what I have. And then I remembered that I got to put my finger on it. So when you put your finger on it, it looks like this, where you can see the fingerprint. This isn't my fingerprint, right? I'm not projecting that. It's from my palm, wrinkles further down, but it's the same idea. It's still a bit messy, though, right? We've still got these horizontal lines that you could see in the original picture, and these are sort of due to the construction of the fingerprint sensor itself. It has these grid lines and this gradient across the whole thing. But what the Windows driver does, and what we can replicate, is it takes a picture from the fingerprint sensor at startup, and then when it actually wants a fingerprint image, it gets that, and it subtracts out the original image to get a much clearer picture. And then what? I have done all this research with the goal of making a Linux driver that will make it really easy. You just install Linux on this laptop on your first day that you have it, and it set up the fingerprint sensor. It all works really easily like it does on Windows. But in doing this research, I've realized that I actually quite like the security model that I've just broken. Right? I don't necessarily want to make foot guns. I don't want to just build into the standard fingerprint sensor libraries the ability to easily, without thinking through what you're doing, have your fingerprint image stored on your laptop where, if it gets hacked, the credential is permanently compromised. So I didn't end up, I do have most of a Linux driver. I can get fingerprint images from Linux. I haven't fully integrated it into libfprint, and I'm not going to, because I don't really think I want to put that out into the world. I don't actually want to have my fingerprint on my laptop now. I've thought about this more. But I think in the process of doing this, I stumbled upon something more interesting, which is the idea of firmware implants in the fingerprint sensor, right? Because when I uploaded this new firmware to the sensor, everything still works, right? I had it registered in Windows, and it still was registered in Windows, and I could still unlock BitLocker and unlock Windows, and if I had it set up, log into Azure AD. And so this raises interesting possibilities for evil mate attacks, right? Because you don't need to negotiate TLS, you don't need to prove you have the PSK to upload the firmware, you can just come up to a laptop, boot Linux from a live USB, even if it's got an encrypted disk on the main operating system, boot Linux from a live USB, and in 20 seconds or whatever, you can have a backdoored firmware on your target's fingerprint sensor. And that firmware, instead of just reading out the PSK, it could save and replay fingerprints. So when somebody comes up to the laptop and scans their finger and then goes away and you come back, you can do some special combination of taps and it'll replay the last good fingerprint to Windows using this trusted channel and unlock their BitLocker Windows Azure AD. Or if evil mail attacks are out of the question, this still means that if you have code exec, then you can exfiltrate the fingerprint image and access other systems that use fingerprint authentication or see what crime scene someone was at. And that's the end of what I did, right? I think there's some interesting questions there, but I decided not to finish writing the Linux driver. So that's my time. Thank you.